Extraordinario, ¿cómo llamamos? De Investigaciones de Impacto Mundial. Today we have the honor to have Professor Måns Henningson from the University of Gothenburg. As some of you might have already seen him giving us the course of symmetries in physics. But today he will talk to us about his research area, which is in particular today, Yang-Mills-Chern-Simons theory and the mass gap. Professor Måns Henningson used to be chairman of the physics department at the University of Gothenburg, at least in the last 6 years that I have been there and met him. He studied at the University of Lund as a bachelor. Then from there, he went to do a PhD at the University of Chalmers. From there, he went to the University of Princeton as a postdoc, and then to the University of Yale in the 90s, I guess. And then he went back to Sweden and I was a professor. And I forgot CERN, exactly, as another postdoctoral stay at CERN in Switzerland. Well, with no more comments on that, please welcome. Thank you for accepting the invitation, and the presentation is yours.
Yeah, this sounds different. Yeah, I'm not sure this is really a good inspiration for young people. This would have been a terrific research program, say 50 years ago. It would have been really close to the research frontier, and it was something you should work on. So say in 1975, I should have given this talk and thought about this problem. I started as a PhD student at Chalmers in Göteborg in 1988. And then already younger people were moving away from this kind of problem. They moved into string theory. I went to Chalmers specifically to do string theory because I read about it in the newspaper. Well, that's where my skepticism against media was grounded. But string theory was a very good thing to work on in the late 80s and the 90s. So I'm very happy I did that choice. Now I meet young people who hear that I have a background in string theory and they are curious and they ask me, oh, how can I get into string theory? And I feel a bit uneasy about it because I don't think you should go into string theory. I think you should have done that when I was your age. So maybe that's my message. You must follow your times. What you should do actually is to look at the internet on the archive. Look at recent papers, see what people are doing now. Pick up some paper that came out last week. Maybe there are some unanswered questions that you could continue to work on. People will be interested in your work. You will get invitations to conferences, etc. Don't try to attack an old problem that was defined already in the 1920s or 1930s, because either it has already been solved, or if it has not been solved, it's for a good reason. It's probably impossible. So you make progress by working on new problems that nobody has had the time to solve yet. Don't try to attack the old classical problems, because so smart people have tried to do that for a long time. And if they have not succeeded, it's maybe not so likely that you will succeed. Or maybe you could do that problem later when you're older. So really, don't follow what I will tell you about now. I'm an old man. It doesn't matter for me. I have my position. I don't need more money, etc. I can do what I wish. So, well, let's continue. Oops, it's dark. Light is an electromagnetic wave, as you know. Described very nicely by this famous fellow, James Clerk Maxwell. I would say the maybe third greatest physicist of all times, after Newton and Einstein. Who is number 3? I think it's Maxwell. And here are his famous equations from 1865. A source of eternal delight to ponder. Well, some of you have close connections to experiment, and you say maybe there's something missing here. Shouldn't we decorate these equations with a little more detail, like constants of nature? And if you're an experimentalist, you wonder what happened to h bar, Planck's constant, the speed of light. I don't know what epsilon naught is called. Maybe the permittivity of vacuum, the electron charge. Funny numbers that have been measured in experiments. I'm a theorist, but for me it looks like this. H bar is 1, C equals 1, epsilon naught is 1 over 4 pi, which maybe not the most common choice, but it's very convenient. Electric charge, 0 should be 0.085. I slipped in a Swedish comma instead of a point. Why didn't I take the electron charge to be 1, since I'm so drastic about everything else? Well, no, I can't. Well, by the way, I love my constants because they tell you that length is the same as inverse energy. Time is also the same as inverse energy. Force would be the same as an energy squared. So square brackets means dimensions. Well, everybody has to agree on the fine structure constant, which is electron charge squared divided by 4 pi times epsilon naught and h bar c, because that's a dimensionless number. You're not allowed to change it. Just as you're not allowed to say, I take pi to be 3 because it's easier than 3.14. Pi is pi. The fine structure constant has an experimentally measured value of 0.0073, and therefore, with all my other choices, I had, how do I point? Not really. Yep. I had to take E like that. A good thing with this E, it's actually much better than having E equals 1. This is a fairly small number. I would be even happy. Sometimes nature is cruel to us. Sometimes nature is very kind to physicists. This is an example of when nature was kind. It gave E a fairly small value, reasonably much smaller than 1. Now, Maxwell's equations are linear, so they are nice to solve. You can build up any solution by taking a linear combination of plane waves that look like this. And this solves the equations, provided that you take the angular frequency omega to equal the modulus of the wave vector k, and also k should be orthogonal to the electric field. So this means that we describe waves that propagate at the speed of light, 1 in my units, and given k, there are 2 transverse polarizations that you could choose for E. You know that light it travels at the speed of light, obviously, and it can be polarized in 2 different ways. This determines the magnetic field. It's not so difficult to quantize this system. Every wave vector k and every choice of polarization, which I call plus or minus, and then we have an angular frequency omega, that system is like a harmonic oscillator. So you have operators obeying these canonical commutation relations. Be aware here that P and Q, P doesn't mean momentum, Q doesn't mean position. It's more abstract. It's 2 things that follow this commutation relation. And then we have a Hamiltonian operator, oops, like this, which I think you're very familiar with. A constant here is a bit arbitrary. You can choose it as you please. I'm sure you have seen these things expressed in terms of creation and annihilation operators instead. So this is what happens for every single wave vector, every mode of the electromagnetic field. Now you can represent these commutation relations in many different ways. Maybe the first we learn about is to take a Hilbert space that's given by square interval functions of a variable q, and then q just acts on this wave function by multiplication, and P acts as a derivative. So prime is just derivative with respect to argument. We have seen this many times. You also know that you can work in, so to say, the momentum basis. So when you have wave function psi tilde that are functions of P instead, Q, and this is wrong, that should be a derivative also here, Q acts by derivation and P acts by multiplication. That's another way to build the same commutation relations. And when you get more sophisticated, you don't want to work with wave functions in space. You say, let's build a Fock space, and then we have basis states that are numbered by n, running from 0, 1, 2, etc. So 0 would be the ground state, and then you have excited states. And equation and annihilation operators step up and down this ladder. You have seen all of this in your quantum mechanics course. So which one should we choose of these? Well, I already hinted that we need not worry. These very clever people, Marshall Stone and John von Neumann, came up with a theory a long time ago. Any two representations of the canonical commutation relations are related by a unitary map between the Hilbert spaces that they act on. So you can work in any representation you wish. It's completely equivalent to any other representation. Just pick your choice. Nothing will change in physics. So more specifically here, if we have wave functions in Q space or wave functions in P space, they are just related by the Fourier transform, which is an example of a unitary transformation. And you know that you can translate between wave functions in Q space for the harmonic oscillator and these Fock space states where you talk about a number of excitations. Well, that's given by some special functions that are called Hermite polynomials. The same here. And you can think out millions of other representations, and there will always be a unitary transformation that takes you back to one of these more famous ones. Let's use the Fock representation. Fock was also a very smart person. So again, you have seen this. You have a basis of states, which I index by the excitation number n. Hamiltonian acting on it gives you an energy eigenvalue, which is just the eigenfrequency omega times n. Remember that h bar was 1. Now, this was for a single mode. Let's go to quantum electrodynamics, which is the quantization of Maxwell's theory. So when I have the following notation, you could have an n photon state, so n excitations, each of which has a particular wave vector, and each of this has a polarization plus or minus. And you build up a state like this, and the energy is just the sum of energies of the different photons. Actually, I even made a sketch of the energy spectrum here. We have a vacuum state with no excitations as energy 0, and then of course we can change these wave vectors continuously, so we can build up any energy above 0 or all the way down to 0 by taking really long wavelength photons. A long wavelength photon has very small energy and nothing below 0. More famous and smart people, Young and Robert Mills. Young is still alive. He's 102 this year. Quick question, how old is Young's wife? She's 48 and he's 102. So I think physics can be a very healthy lifestyle. Young and Mills many years ago wrote down a generalization of Maxwell theory. This can describe, for example, quantum chromodynamics, the strong nuclear force. Here are the equations. They look very similar to Maxwell's equations, except that the derivative here, I call it d. That's a bit tricky. I hide some things in the definition of d. Some other differences. All of these variables that you see here, they're not numbers anymore. They are matrices. This rho and the j, that's charge density and the current density. They can describe quarks that carry something we call color, or anti-quarks that carry anti-color. And these E's and the B's, the so to say electric and magnetic fields, they describe gluons, the things that hold quarks together. Also, gluons are colored, or rather, they have both color and anti-color. I call it bicolor anti-color. But it's a bit deceptive as I wrote it. I mean, this looks like Maxwell's equations. I just changed some symbols. But actually, there are hidden non-linearities in the definition of E and B, and also this so-called covariant derivative. So if you really write out the equations, what they mean concretely, they are non-linear equations. You can't just add solutions as you do for Maxwell theory. The non-linearities are controlled by a coupling constant E, which is the analog of E that we have in electrodynamics, the thing that was 0.085. Now, in quantum theory, this becomes very complicated. It turns out that you can't really say what E is in the quantum theory. The value that you should use for E, the effective value, depends on the energy scale, capital E, of the process that you are considering. If you want to use this theory to scatter, say, protons against each other, you must first ask, what energy do my protons have? And then you should insert an effective coupling that looks like this. Lambda is a characteristic scale for quantum chromodynamics. It's about 300 MeV. So this is a bit of a mystery, because the original equations didn't have any particular scale. Now that has just appeared by miracle. Anyway, you can look at this formula and you see that if you consider processes at very high energies, this logarithm will be big, and 1 over the square root of it will be small. So if you do high energy processes, the theory is fairly similar to Maxwell theory. You don't have to care about the nonlinearities. And that also means that we understand the high energy theory really well. But if you go to low energies, you see that as the energy approaches this scale lambda, about 300 MeV, the logarithm becomes 0. 1 over square root of 0 goes to infinity. So when the theory becomes strongly coupled, we don't understand a thing. We have to really throw up our hands. And that's what makes this problem so extremely difficult. There are some people that worked very successfully on it and got the Nobel Prize. Martinus Feldman and Gerhard Tuft proved this renormalization property. David Gross, David Politzer, and Frank Wilczek a few years later showed this thing that with the coupling constant going to 0 at high energies. Here's a challenge to you, although I don't think we should work on this problem. Find a rigorous definition of Yang-Mills theory, and you will get your own Nobel medal. And now, for most of you, you will get even more. I mean, I can promise that you will get this if you find a good definition of Yang-Mills theory, really, at quantum level. Most of you, but not you, Remy, will also get the mathematical fields medal. But there's a cutoff in age, and no, you're more than 40. Yeah, so work on something else. You will only get a Nobel Prize if you solve this problem. So what do we want to understand? Well, we have some empirical facts about Yang-Mills theory at low energies, even if we have no theoretical control of the theory. For example, quarks and gluons can never be isolated. If you try to kind of break them apart or take them away from everything else, it doesn't work. They are confined. I think here I want to show that you have two colored particles and you try to pull them apart, but at some point you just pair create new particles. So the only thing that can appear in isolation are colorless combinations. Colored things can never be isolated. That's called confinement. Also, as an empirical fact, we can look at the energy spectrum. And we have a vacuum state with nothing in it. It has zero energy. But when we don't have any states until we get up to some specific value m, which was on the order of this lambda, which was 300 MeV, and then we have a continuum. But it's really empty here in the middle. It's a gapped spectrum. No good theoretical explanation for that. And indeed, understanding this problem in free spatial dimensions and time dimensions appears extremely difficult. So what can you do if you want to think about it? Maybe we could change the dimension of space-time. At least as theoreticians, we're always allowed to do that. Think about Coulomb's law. The Coulomb force, that's the electric charge, I mean the Coulomb force between, say, two electrons. It's the electron charge squared divided by the distance raised to the power d minus 2. With free spatial dimensions, capital D would be 4, and here you get the usual 1 over distance squared fall off. But this is different in higher dimensions or lower dimensions. But now force was the same as energy squared, distance was the same as energy to the minus 1, so you can work out that this coupling constant E has the dimension of energy to the 2 minus d half, or if you wish, length to d half minus 2. So it's only in 4 space-time dimensions that the coupling constant is dimensionless, for example 0.085. In other dimensions, it's not just a number. How much time have I got? Half an hour? Yeah, I haven't numbered the transparency, so I don't really know where I am. We'll see what happens. Also, let us point out that in 4 space-time dimensions, a photon or a gluon had 2 different polarizations. I call them plus and minus. It means a photon propagating in that direction must be transversely polarized like that or like that. There are 2 orthogonal directions. If you have fewer or more spatial dimensions, you will have fewer or more transverse polarizations, always d minus 2. So let's see what happens. Let's start in high dimensions, more than 4. Then you see that this coupling constant will be some positive power of length. So that means that if you are at really short distances, the coupling constant will be important. That probably means that Yang-Mills theory can't be a fundamental theory. Or at least if it's the right theory, it will be completely impossible to understand at short distances. There should be some other description at the really shortest length scales. So common wisdom is that in more than 4 spacetime dimensions, Yang-Mills theory could only be an approximate low energy description to something else. Maybe string theory, if you insist on working on that. And you could have Yang-Mills theory as kind of an approximate low energy description. But it's nothing for somebody who wants to investigate a fundamental problem. So let's go below the usual spacetime dimension. Well, if you're in 2 spacetime dimensions, which means a single space dimension and time, well, then you have no polarizations at all. You have nothing that looks like a propagating photon. There is some interest to that theory, but I'll not cover it here. So we are left with 3 dimensions. The coupling constant would have a dimension of a square root of energy. That means that if you are at really short distances, that means that you are looking at problems that are with high energy, then you can probably neglect the coupling. So the theory will be really easy to understand at short distances. But if you go to long distances, that means you scatter particles with low energies, then this coupling will be really important. And you again have a difficult problem. We don't have an analytic understanding of this theory, but there is a strong belief that also this theory will have a mass gap. And then by dimensional reasons, the mass gap m must be proportional to the square of this coupling constant. since the coupling constant was of dimension square root of energy. Let's write down the Yang-Mills equations again. I simplified. I removed the quarks from the right-hand side. Looks a little bit different. I should note some things. First of all, Maxwell's equations used to be 4 different equations. Now that we are down to a smaller dimension, one of the equations is completely trivial. We get it for free, so I only write out the 3 non-trivial equations. Note also that in 2 spatial dimensions, in 1 time dimension, magnetic field is no longer a vector, it's a scalar. Also, there is an operation you can do in 2 spatial dimensions. You could dualize a vector to another vector. Also, you have various operations here. This d here is something like a rotation. This d here is something like divergence. This d here is something like gradient. Rotation of a vector, we are used to this being a vector, but it's actually a scalar when you are in 3 dimensions. So all of vector analysis looks a bit different, but you can get used to that very quickly. It's not really in this slide, but if you take the cross product of 2 vectors, we are used to that being a vector. Here it's scalar. Again, this is a very difficult theory to understand, but maybe it's a little bit easier than the real physical case. I will outline a project which is much more modest, which will not give me any kind of famous prize or anything. What will I do? First of all, I will not take space to be infinitely extended. I will take space to be some compact manifold, something which doesn't have infinite size. This is time, and this is space, which now is compact. And then what do I want to do? Well, I would like to compute the energy spectrum of this theory. And since I'm on a compact space, I expect the spectrum to be discrete. I should have energy eigenvalues. And I will not do even that precisely. I will do it in perturbation theory. I will do it as a series expansion in this coupling constant E, and I will only go to order E squared. Now, to follow the argument, it might be convenient to take this 2-dimensional space M. I start with some reference space, maybe a space that has unit area, like a unit sphere or something, and then I scale it with some factor R. So R is something which has length. And then just by dimensional analysis, you'll know that all the energy eigenvalues E must be of the form E squared times some function of this dimensionless combination. So E squared R is dimensionless, and you can take any function of it when I insert E squared here in front to build something of dimension energy. This reference space M0 could be anything, and I went to a bakery shop to find examples. Well, it could be a sphere, a chocolate ball. So it's the surface that counts. We want a 2-dimensional space. It's the surface of a chocolate ball. It could be a donut. It could be a pretzel, or it could be something more complicated that you pick up from the bakery shop. Anything is allowed. But you see that they are not infinite, they are finite spaces. Well, if you want to make concrete computations, probably you should take this space M to be a flat torus. I don't know if people are aware of this being a torus. This is actually similar to this one. You identify this side with this side, and that side with that side, so kind of double periodic boundary conditions. Just like here, you can go around, it's periodic around that direction, and you can also be periodic around the other direction. It can be even simpler. Let's take this parameter tau to equal I in the complex plane, so it's a square, it's a unit square. And then the possible momenta, just like in solid state physics, they are given by integers. So I would be a vector with integer entries, and then we insert 1 over R. R was the thing that we used to blow up this space as a length scale. Naively, when you look at it, you have a Hamiltonian operator that looks at most Hardwick. But this is complicated. This theory has some redundancy called a gauge invariance that you have to fix. Also, one of the equations looks like Gauss' law. That's not really an equation of motion. That's a constraint. You have to solve that. You have to parameterize the solution to this in some convenient way. This is actually my own very modest contribution to the field. I invented a parameterization of it last year, which I presented in a talk that we had online, which you probably didn't attend, so never mind. It's not important. When you do all of this, it turns out that the Hamiltonian operator is actually not quadratic. It's an infinite series in the coupling constant E. And in fact, the terms here, the thing here that is independent of the coupling constant consists of two terms, one which is bilinear and one which is a constant. This one is a cubic term, and this one falls apart into a quadratic term, a bilinear term, and a constant term. These are easy to read off from the classical theory. These are ambiguous because the constants alpha, beta, and gamma, that's also normal ordering constants. They have to do with in which order you put your operators. Just like for the harmonic oscillator, you know that there might be a 0-point energy or there might not. It's a bit your choice. So beta and gamma, alpha, beta, and gamma are not really determined yet. Okay, so when we build a Hilbert space, we have a basis here. This is like an n-gluon state. And this is an energy eigenstate. And the energy is just the sum of the individual gluon energies. So 1 over r, 1 over the size of the space, comes in here as a prefactor. And then you know from quantum theory that you can compute the exact eigenstates. Put a small e here. Here I had a 0 for the free eigenstates, and here it's the interacting eigenstates. So these are eigenstates of a free bilinear part of the Hamiltonian, and these are supposed to be eigenstates of the complete Hamiltonian. And the energy eigenvalues are given as a series expansion in the coupling constant. So this is very standard quantum mechanics. You could just look up in the textbook how to construct these interacting eigenstates as a power series. I think you have seen this formula or maybe in slightly different notation. Okay, as it stands, this state is not normalized. Well, you can compute the norm, and then you could just divide by that norm to get a normalized state. But oops, this sum here diverges. This is a really bad surprise. So this doesn't make sense. This state here, the interacting eigenstate, is not normalizable. It's not part of a Hilbert space. We can't use it. What has happened? Well, that was explained by Rudolf Haag also many, many years ago. He said that this will always happen in quantum field theory. You are not used to it if you study quantum mechanics, because the formula I showed you on the previous slide always works in quantum mechanics, but it doesn't work in quantum field theory. And actually, this Stone von Neumann theory fails when you have infinitely many harmonic oscillators. So that means that the canonical commutation relations can be represented in different ways, and these ways are truly physically different. They can't be related by unitary transformations. So rather than saying that we have a single Hilbert space, which kind of can accommodate both the free theory and the interacting theory, you must have a separate Hilbert space for each value of a coupling constant. So what can we do about this? Well, here's my suggestion, well, I came up with it myself. I hope it works. Let's say that these free eigenstates and the interacting states, they live in the same vector space, but now I call it V. I dropped this thing with having a Hilbert space. So I dropped the idea of having an inner product, a norm in this space. I just see them as elements of a vector space. Then you know that your equation and annihilation operators, they act very, very easily here. The equation operator adds an extra gluon indexed by I. The annihilation operator takes away a gluon. So this hat over it, over IM here, means that we removed gluon number M. This is something like multi-particle physics. Now you can rewrite this in the interacting basis. So this is just another basis for the same vector space. And then these, so to say, creation and annihilation operators have a more complicated action, which I have not bothered to write out because it wouldn't really fit in the transparency, but it's very concrete. It's not just adding or removing a gluon. You also get corrections to these formulas. And now we just declare that this space here is a Hilbert space, and we define a norm that must be compatible with the canonical commutation relations. So here we have, so to say, 1, and here we have alpha alpha dagger minus alpha dagger alpha. Alpha alpha dagger minus alpha dagger alpha should equal 1 by the commutation relations, so that's why we get this thing. And then we could just postulate that the vacuum has norm 1, and all other norms will follow recursively. So to say, we started with a Hilbert space, and we said, oh, this doesn't really work. Let's forget that it's a Hilbert space. We drop the Hilbert space structure and take it as a vector space. We see the relationship between the free and the interacting states as a change of basis. And then we rebuild it to a new Hilbert space with a new norm. And this norm will be different for every value of the coupling. And then we have a formula for energy eigenvalues, and this is also something that we have seen in quantum mechanics many times. Another divergence term, but now we are more confident. We say if we solve that first problem, we can probably do something about this. And I think that if you use those undetermined normal ordering constants in the second order part of the Hamiltonian, I think you can fiddle to cancel these things. Now, if x is any finite number, x minus x equals 0. So infinity minus infinity equals 0. Let's just take the x goes to infinity limit of this equation. You'll believe me? Infinity minus infinity might be the cubic root of 2 plus pi 2 over 6. Yes, yeah. You agree with that one. Let's take that one. Or something else. So clearly, whenever you have infinities in physics, and they happen all the time, you must be very careful. Then you must think about which symmetries do you have in your problem, which properties are important to you, and you must make sure that you preserve those properties. You must regularize this sum, for example, not taking all the terms at the same time, but adding one term after another, and we're doing the same with the divergence here. And during that process, you must make sure that you keep the properties that you love. And maybe some properties will be lost. But you must do this carefully so you don't kind of throw out the child with, can you say that in Spanish, throw out the child with the bath water? No? Yeah, maybe it doesn't make sense in Spanish. Well, you must make sure that you don't lose the things that you really care about. I'm not finished with that, but I think that this can be done. And then I think that we arrive at a concrete formula for the value of the energy of the n-gluon state. It will be the free value, and then we'll get corrections that I think we can get very concrete results for. So second order the coupling constant, and then higher terms that somebody else can compute if they wish. I'm not going to do it. I divided it in 3 parts here. We have a single gluon energy contribution. We have something that describes the interaction of 2 gluons, and we have something that describes the interaction of 3 gluons, and when we don't have anything more. So compute this script E, script F, and script G, which I think can be done. And you have a very nice formula. And you say, oh, this famous mass gap, isn't this what you see here? Because here you see you have 1 over the size of the space, and then we have something that is independent of the size of the space. So very good. Let's now take the space to be very large. Then you see that this term goes to 0, but this will remain. So maybe this is the mass gap. Oh, I don't think so. I don't think I can make progress on the mass gap in this way. Of course, the omitted terms here, that's a power series in E squared R. And this power series presumably only works if the E squared R is reasonably small, not much larger than 1, maybe smaller than 1, I don't know. Well, so take a fixed value of a coupling constant and make your donut or your chocolate ball or whatever very big. This will be a big number and you can't use the theory. So no, I don't think I can say anything about the mass gap. Also, which states can we apply this to? I have suppressed everything having color here. You don't clutter the formulas. But if you take color into account and look at states that only have 1 gluon, we said that gluon had this bicolor anticolor, so they are not colorless. Therefore, they are not physical. You can't isolate them. It doesn't make sense to ask what energies do they have. But if you take 2 gluons, then actually for each value of these momenta, there will be a colorless state that is physical, and you can compute the energy of it. And the same if you have 3 gluons. If you have more than 3 gluons, it depends a bit. You can come up with a formula for the number of colorless combinations, but I don't care. I'm happy to see that there is a sensible physical problem to compute the energies of these 2 gluon states and the 3 gluon states. The title promised something about the Chern-Simons interaction. So here are Chern. He passed away some 20 years ago. He was a student he was the thesis advisor of Yang. Jim Simons died very recently. He was was a really rich guy because he had kind of a short attention span. He worked in mathematics for some time and then he got tired of it, and then he left academia and started a hedge fund called Renaissance, and then he used all his math skills to predict the stock market much better than anybody else. So he became immensely rich. So what did he do with his money? Well, he gave it back to science. He was a great philanthropist, very considerate of other people, something which I think he learned from Chern, who was also a very nice person, did I say. Anyway, in precisely 2 spatial dimensions and 1 time dimension, you can admit some extra complications to this theory. You can, so to say, introduce a right-hand side to the equations, but it's not a right-hand side that is carried by quarks or antiquarks. You see that here on the right-hand side appears the magnetic field and the electric field, and also a parameter kappa, which has to be an integer. It's kind of a quantized parameter. When you can work out classically, can you do what do the solutions look like to this equation? And at weak coupling, you can have plane waves, but they have a different dispersion relation. Angular frequency is now not proportional to the modulus of k, but you see something that you recognize from special relativity. This looks like a massive particle, and indeed you have a mass of gluons in this theory that's given by E squared times this integer kappa. Here I attempted to expand this as a power series in kappa. And also in the quantum theory, you see that you get an extra term here. Never mind the details. I put in this slide mostly because I had it in the title and I didn't want you to go and leave this talk and feel cheated. Let's summarize. Yang-Mills theory is extremely important in elementary particle theory. I talked about gluons and quarks here, but actually Yang-Mills theory describes everything. It's a generalization of Maxwell theory that covers electromagnetism, the weak nuclear force, the strong nuclear force, everything except gravity. But even if this theory is so important physically, we don't really understand it. There is no formal good definition of it. It's just a cartoon, what I've shown you. So what we have done here today is to discuss a small project with simplifying features. First of all, take down the space-time dimension to 3 instead of 4. Then compactify space. Make it a donut or a pretzel or something, but not infinitely extended. And this is to have a discrete spectrum of energy eigenvalues. And third, give up for the time being of finding an exact solution. Try to do this in perturbation theory as a power series in the coupling constant, and just the lowest order. Okay, I haven't given you the final result yet, so it's not completely trivial. I think that's all. This is a painting by a Gothenburg artist. You like the painting? Actually, it's hanging in my living room. Original, yes. I mean, she is kind of medium famous. It's a female artist. She's not one of the top people in Swedish art, but reasonably famous. And I like the painting, and I bought it. And I'm so happy that you love it. Gracias.
Thank you, Professor Henningson, for the nice talk.
You can call me Måns, that's fine.
Måns, okay. Yeah.
Yeah.
Questions? No? Everything is clear? Okay, Thomas.
I have a question. I never worked in this area, but so about
Georg Freilich? No, not Georg Freilich. Huh.
That he showed that 2 dimensions we don't have the divergence either.
No.
Which seems to be the very wide value.
Sorry, are you talking about two space? Well, you do have divergences in 2 dimensions, but they are milder than in 3. Yeah, so yeah, that's the reason. Problems are milder in that dimension, but they are not completely absent. And the theory is still highly non-trivial.
Thank you. Any other question? No? In Yang-Mills theory, I mean, at least the way that I long time ago kind of remember, of course, you always deduce it through a Lagrangian.
Yes.
And then, of course, the main point is renormalization theory.
Yeah.
So I kind of saw that this renormalization that you're saying here is through perturbation theory, more like in classical, or not classical, but well, as we do it in quantum mechanics.
Yeah.
So in this case, this band gap that you show at the end, of course, you have the mass, but you say that it also is not sure that you have gotten this mass gap result because you're missing the other terms.
Yep.
In this case, this renormalization that you're using will affect all the perturbation theory that you have, or is only specific to the case that you have?
No, it will affect all the terms, so there will be more effects at each order in perturbation theory. Well, you started by saying Lagrangian, and I used the Hamiltonian framework here. It's true that 99% of the work that is done in Yang-Mills theory or quantum field theory is done in a Lagrangian framework,
Exactly.
and you use the Feynman path integral. And typically what you do is that you look at scattering processes with particles coming in from afar and scattering against each other. And it's very nice to work in a Lagrangian formalism because you preserve Lorentz covariance. And renormalization is proven. Well, I said, but when you have infinities, you must make sure that you keep the properties that you love. And when you do renormalization in a Lagrangian framework, you make sure that you keep Lorentz invariance. I'm making life much harder here by using the Hamiltonian formalism. But that's because I don't have Lorentz invariance anyway, because my spatial manifold is a pretzel. And then I have time, which is infinitely extended and goes from before Christ till 2038 at least. So I don't have Lorentz invariance. So that makes it more difficult here to renormalize because you don't really know what properties you should preserve. On the other hand, the Lagrangian formalism and the Feynman path integral is not well adapted to solving for the energy spectrum. That's not the kind of question that you typically pose in quantum field theory. You do scattering processes, you don't do energy spectrum. So no, this is different. And this gives me some hope that maybe I have a small niche for an old man to do some work here, because 99% of the work has been done in other directions. So that's another advice to the young people. I told you, look at the archive, find some recent paper that looks interesting, see if you can go beyond that, but obviously don't go in exactly the same direction as everybody else. Find your slightly awkward other twist to the problem where you can kind of have your private little garden, at least for a while.
Your little contribution.
And make your contribution. And then when you feel more safe, you can challenge a kind of more mainstream problem. It's a balance. Finding a problem that is slightly off the beaten track, but still interesting to other people, because you should not do something that nobody cares about because you will never get a job.
But still, I mean, I would like to complement that part with, before I pass the microphone to Thomas. You learn Yang-Mills theory of quantum field theory because it's a tool that you learn if you want to go into this field theory or a standard model.
Yes.
Not because you want to make a contribution in Yang-Mills theory, but because it's the tool that you learn to do something else. It's like learning precisely as you started, electrodynamics. I mean, it's a almost 2-century-old theory. We learn it because we know how it works, but not because possible somebody will make a contribution in electrodynamics. I don't know that, but it still is a tool. And I think that in that sense, it's worth it to see something how it's done. As you said, there are many varieties of Yang-Mills theory. Maybe something of one of these guys is the next smart Newton or
Absolutely.
Einstein.
I mean, well, no, it's not probable that one of you are the next Einstein, but I think you're smart people and that you could do significant contributions. Actually, I can correct the story a bit, Remy. No, I didn't learn Yang-Mills theory in the beginning. When I started as a young person, string theory was the thing you should do. And the senior people told me, don't waste too much time doing quantum field theory. That's something we used before, but it will be superseded by string theory. If you learn string theory, well, that's better. You will see that quantum field theory is only of historical interest. That was not true. So there was a long delay before I actually picked up the basics of quantum field theory and Yang-Mills theory. And now I'm not so interested in making contact with experiments because it's too much work for phenomenology, etc. I'm interested in kind of more this foundations of a theory. How can we define it? Therefore, I'm happy to work in free space-time dimensions. That's not the physical universe, but it's good enough for a mathematical toy model. That's what I'm doing. Yep. Well, please.
Would like to comment.
Not much. Not much. Okay.
Anyway, I had to.
Ah, yes, yes, yep. I can imagine. Yeah. Mm. Yeah. And that was probably very wise advice. General relativity was a fairly dead subject for a long time. Not today, because it has been revived. Things go up and down.
Yes.
No insult, Remy, but atomic physics was a little bit dormant at some time, but now it's really up, and you have these wonderful laser things and so on. No, things go up and down. So follow the tides or follow the surf wave. Yeah. Yeah. Yeah, or new theories. Somebody comes up with a new smart theory, and then you have millions of questions that are accessible. But it's very difficult to work in an old theory.
Any other question? Yeah, Alex, let me get them.
By the way, Mellor died fairly young, I think. Or am I mixing me up with somebody? No, when I'm probably mixing it up. No, not very young, no. Well, I'm mixing him up with somebody else in Denmark. Yeah, please.
Hi, thank you for the talk. I have maybe a naive question. The Yang-Mills theory can be constructed to any kind of semi-simple compact Lie groups? Or
Yes.
why?
Yes.
So there's no unique Yang-Mills theory. And what's the reason to be SU3, U1? There's a physical reason to choose this.
Well, SU3 means that there seems to be three colors, so to say. Take color very metaphorically. There is not really something like a red quark or a green quark or a blue quark. It's just a metaphor. But we say that there are three colors, and therefore we use the group SU3. If you are following my lectures on symmetries, well, we touched a bit on this. SU3. It seems to be an experimental fact that we have three colors. Nature could have chosen something else, but it seems to be free. But mathematically, you could use any number of colors or any other compact semi-simple gauge group. Absolutely.
Oh, thank you.
Any other question? If not, let's thank Professor Måns Henningson for the nice talk.
Thank you.
And we can continue the discussion outside.